All right, let's talk about how we use all of the kinematic equations that we have developed. Maybe do some examples using kinematic equations. We'll start with the easiest equation, which is usually written like this, just d equals vt. Now, just as an aside, when you read in textbooks, you often see the little vector sign, the little half arrow, written over top of velocities and displacements and accelerations to remind us that these are vectors. However, I find that it really makes things look a little bit more confusing. And I go by the general rule that everything in physics is a vector, because it is. And there may be certain times when we only want to consider the magnitude of one of these things, but everything is a vector. We always have to expect that there's a direction involved, and we always have to think about both the magnitude and direction. So that being the case, I'm not going to put little vector signs, but we're going to understand that everything I write on the board is a vector. Even time, technically, is a vector because it has a single direction of forward. But we won't get into that. Here's our simple equation. Displacement is equal to velocity times time. It's the product of velocity and time. Some people like to build a little triangle so they can solve, and they put displacement on the top and v and t. I don't like to use that either. I like to rely on our good old friend algebra, which actually makes your life simpler when you get the hang of it. So this is the only version of this equation I'll ever use. I won't rewrite it as v equals d over t and t equals d over v. That just means I've got more equations to worry about. As long as I keep this equation in my head, algebra will make sure that I never make a mistake. So this equation has one very important limitation that you must remember when you use it. It's an equation that describes constant velocity, an object that is not changing its velocity. So what does that mean? Well, it means the object is not speeding up or slowing down, and it also means the object is not changing directions. So even if you traveled at a nice constant speed of 4 meters per second, but you turned and changed your direction, that is technically still changing your velocity. And so you can't even use this equation to represent that, even though it seems like you could. You could only use this equation when you have a situation where there is no change in the speed or the direction of the object. Constant velocity. If you have a change in velocity, then you have to use one of the other equations that we'll deal with in a moment. Here's a simple question to give us the idea of how we could use this. The dog walks 6 meters in 4 seconds. Whoops, I said 6 meters and I wrote 6 minutes, so I'll fix that up. The dog is not going to walk minutes, of course. He's going to walk 6 meters in 4 seconds. And the question we might want to know is, how fast is the dog going? Now, here's a question where the direction doesn't really matter all that much. In fact, what we do when we solve this question is we just assume that whichever way the dog happens to be going will be the positive direction. Because remember, we can assign any reference frame we want to any question. So, and we do this all in our head. We don't even have to think about it. So if we wanted to draw a little picture, we could say the dog starts here and then he runs or walks over here to another spot, so point A to point B, and he is going to run 6 meters. And we know that there's a certain amount of time involved in doing that. The time involved in doing that is 4 seconds. And so what you can do is you can write a little list of the information given in the question. I see that it's giving me a displacement of 6 meters, and I see that it's giving me a time of 4 seconds. And so it's asking me how fast, which of course is the speed or the velocity, so it's also indicating that I have to somehow involve that. And then once I have my little chart of numbers, I can see that those three things go together nice neatly in the equation d equals vt. Now it doesn't matter that I'm looking for a v, and my equation is it looks like it's telling me what d equals. That doesn't matter, because we're just going to put the numbers where they belong. The d number goes where the d is. That's 6 meters. And we won't put any units in here, because the units will confuse us with the variables. Like meters is an m, but so is mass when you do other questions with force. And it gets all confusing. So as a general rule, we won't put the units in, but you'll notice I put the units in my list up here. And I made sure that they were all standard units. As long as you use standard units, everything works out wonderfully. Now, next thing is a v. Well, look, I don't have a v. This is missing. So that's what I'll just leave as v. But I do have a time, and the time that I have is 4 seconds, so that's going to go over here where the t is, and I put the 4 in there, so v times 4. Remember that brackets in algebra mean multiply. Now, how do you solve this equation? Well, you want to figure out what v is, so you use the rules of algebra that you learned in grade 7, 8, 9, 10, and you remember that you can do anything you want to any equation as long as you do it to both sides. And since the v here is being multiplied by a 4, I can sort of undo that if I divide both of these equations by 4. And by doing that, v times 4 divided by 4 just ends up being v again. So we kind of say that the 4's cancel. I'm not a big fan of the word cancel, but they do divide out. Now what's 6 divided by 4? Well, that's the same as 3 over 2, which is 1.5, isn't it? 3 halves is 1.5. And so that would be 1.5, and then what would be left is the v. And of course, this is the point when I should put in my units. Meters per second is what goes with velocities. And so it's telling me that the little dog was running 1.5 meters every second. Now, let's go back to our picture and see what that means. Well, it means that if I divide this up into 1.5 meters, right, I will get 1.5, and then 3, and then 4.5, and then 6. And so in the first second, after 1 second of moving, I went 1.5 meters. After another second, I went an additional 1.5. Oops, I think I made a mistake here. Let's go back and check that out. 1.5. Oops, I lost my spot. In the first second, if I went 1.5 meters in the first second, 1.5. In the second second, I went another 1.5. And then, well, that's going to be okay. I didn't make a mistake. I saw that 6 there, and it made me worried. If I go again in the third second, 1.5. And then the fourth second, another 1.5. So this is after 2 seconds, 3 seconds, 4 seconds. So there we go. I've done every second that's gone by, I've added 1.5 onto my displacement. And the total of all these, of course, is 6, the total distance from A all the way to B. But that's a very simple equation, and it's a very simple way to use it. And of course, you can use it to find the D or the V or the T, as long as you understand how to use the algebra. Put in the numbers and work it out. All right, the next equation that we learn is an equation where you do have a changing velocity. And this equation comes from the slope on a velocity time graph. It tells us that the acceleration is equal to the change in your velocity compared to the change in the time, or how long it takes. And we often write delta V as V2 minus V1, which is, some books say VF for final speed, take away VI for initial speed. Doesn't matter. It all means the same thing. Remember, these little subscripts are just for us physicists to keep track of our numbers and know what they are. They don't have any mathematical value. So you can call them what you want. I tend to call it 2 and 1. 2 is the second speed in the question, and 1 is the first speed or velocity in the question. And so we divide this by the change in our time. And the change in time is also t2, take away t1. But I find that whenever I time something, I always start my stopwatch at 0, because that's the most convenient. And that means that t1 is always going to be 0, and t2 will always simply be the time that has passed. And so I tend to write this in a little bit simpler form, v2 minus v1, just divided by the time that has passed, or the time that it's taken to change the two speeds. So this is the second equation that you learn, and it is a slope equation. Oops. It is a slope equation, which means it's talking about the change in one object with relation to time changing. That means that it's a rate of change. Okay, and we saw that, and we've seen that in a different video. Let's do a question where we might use this particular equation. So we start off with, this time we'll use a cat. A cat is walking at 2 meters per second, which is actually a pretty fast walk, but we'll call it walking, when it suddenly speeds up, or it begins to run. Or we could use the word, it begins to accelerate, which means it's going to speed up. If it reaches a speed of 6 meters per second in 6 seconds, so it takes 6 seconds for it to speed up to this 6 meters per second. What is the rate of acceleration? What is the acceleration? What is the cat's acceleration? We'll put cats in there. So we want to know how we would describe this acceleration rate. And so when we look at the question, we start by looking at the information that's given. The first thing it tells us is the cat is walking at 2 meters per second. I just realized that I made an error on that, and I don't know why that little square got in there, because that's not an acceleration, it's a velocity. So sometimes my brain works a little bit behind my fingers, and we get those extra glitches. So that's a velocity, and that would be what we would call the initial v1. So I'll make a little chart. v1 is 2 meters per second, and I write the unit in so I can check for standard units. Then I keep reading when it begins to accelerate. Well, that tells me that something. It tells me there's going to be an A involved in this, but it doesn't tell me what it is. So I'll put a question mark for that. Then, if we keep reading, we see that it says, if it reaches a speed of 6 meters per second, that tells me that's the second speed in the question. So I'll write down v2 is 6 meters per second. And then it says in 6 seconds, which is telling me that the time is 6 seconds. And then, of course, what is the acceleration? Well, it's telling me that that's what I have to find. And so I have to look through my formulas, my toolbox of formulas, and I look for a formula that happens to have all of these things in it, because these are the things that are being described in my problem. And it turns out to be our friend that we just finished discussing, v2 minus v1 over t. I put in the numbers wherever they belong. In this case, I don't have an A, but I have a v2, 6. I have a v1, 2. And I also have 6 seconds. You have to be careful. Sometimes you'll get the same number and it can be confusing, but you have to watch. So now I just have to work this out. 6 take away 2 is 4 over 6, and 4 over 6 reduces to 2 over 3, 2/3. 1/3 is 33.3, so 2/3 is 66. So we put 0.6, and if we round it off, it's about 67 meters per second squared. That's the unit for acceleration, not for velocity. Don't make my mistake. Now we can also use this equation to do a different example. We'll take, what if we didn't know something else? What if we had a question where it said a bat? Not a baseball bat, but a mammal bat, the one that flies. A bat is flying at 2 meters per second. If it accelerates at, we'll make it a fast acceleration, 3 meters per second squared, which I guess is reasonable if you're flying. If it accelerates at that rate, wait a minute, let me erase that. If it accelerates at 3 meters per second over 8 seconds, how fast will it be going? How fast will it be going 8 seconds later? Okay. In fact, maybe a better way to write that, to make it sound a little bit clearer in your mind, is to put what I was thinking, I think originally. If it accelerates at 3 meters per second squared, how fast will it be going after 8 seconds? Maybe that makes it a little bit more clear to understand. So there's our question. So we read the question, and we see that the bat is flying at 2 meters per second. That's telling us our V1. It's beginning at 2 meters per second, the initial velocity. Then we read a little further, and it's telling us that it's accelerating, and this time it's telling us how much. So that's an A, and that is 3 meters per second squared. Then the next thing it says is, how fast will it be going, which is telling us that it looks like we're going to be searching for the second speed. How fast will it be going? And of course, we have after 8 seconds. So we have a time of 8 seconds. All my units are the right ones. They're standard, so I don't have to change anything. But this would be the time to check every one of your units and make sure that they're standard units. And if they weren't, you would have to convert them. And now we still have our little friend, V2, take away V1 over T. Now, it doesn't say V2 equals, but that's okay. All of these things are in there, and that's all that matters. As long as everything is mentioned in the formula somewhere, then the answer will emerge with algebra. So where does well, we have an A here. So the 3 goes where the A was, because the A was a 3. The V2 is something I don't know, so it stays V2. The V1 is a 2, so it goes where there, and the time is an 8, so it goes over here. Now I have to solve the equation. So what I do is all the rules of doing the same thing to both sides again. First, multiply both sides by 8. Now if I multiply the other side by 8, you multiply all this by 8, you just divided it by 8 right here. So if you divide by 8 and multiply by 8, then everything is gone. And so you might have 3 8s or 24. You might jump right to here. Many of you will probably not even bother with this step because you can kind of do it in your head. So you might go right from here down to the next step, which is fine. The more algebra you do in your head, the smarter you will become. And so 24 then, we add 2 to both sides of the equation. I'll do the both steps for you. Why do I add 2? Well, because here I'm subtracting 2. And remember, I'm trying to get this V2 all by itself, try to isolate it. So if there's a -2 there, I can eliminate that by adding 2. And as long as I do it to the other side, it's still equal. And so you can see how -2 plus 2 disappears. Right? And we have 24 plus 2, which is 26, equals V2. Now 26, and since we're done, I'll squeeze my unit in here, meters per second. That's pretty fast. This bat has gone from an initial speed of 2 meters per second all the way up to a speed of quite high speed of 26 meters per second. Now what does that mean? Well, if he starts at 2 meters per second, and every second that goes by, he actually goes 3 meters per second faster. So let's just draw a little picture of that to help us understand what this means. Here's our bat. Here's 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6, 7, 8 seconds. Those are our seconds on there. So in the first second, he was going 2 meters per second. But the acceleration rate is 3 meters per second. So that means you add 3 meters per second for that second, and then add another 3, and then add another 3, and another 3, right? Every second that goes by, you're adding 3 meters per second to your speed. And so what are you adding? Well, you're adding 3, 6, 9, 12, 15, 18, 21. 1, 2, 3, 4, 5, 6, 7, 8 seconds. So you're starting at 2 meters per second, then you get to 5 meters per second. Then you'd add from 5 meters per second, you would, in the second, you'd add the next 3 and get 8, and then get 11, and then you'd add the next 3 and get 14, and then you'd add the next 3 and you would get 17, and you'd add the next 3 and you'd get 20, and you add the next 3 and you'd get 23. And we should be at, after 8 seconds, we should be at 23. 4, 2, did I make an error? Oh, I know what I did. I forgot the other 3. We forgot the 0, because going from 0 to 1 second is also a second. So we need one more little spot right here, and that's where we would add another 3 seconds and get to the 26. Right? So from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. That's right. So we lost that little guy at the start. But you can see what that means. You're adding 3 meters per second to your velocity every second. So of course you're going to get going pretty quickly, and this little bat obviously is. And that's the end of this video. In the next video we'll talk about some of the more complicated equations that involve displacements and velocities and accelerations.